Today we're going to start talking about two different applications of exponential growth and decay functions. And both of them basically use more or less the same formula here, which is y is a times either 1 plus or 1 minus the r raised to the t power. Now, if a real life quantity increases by a fixed percentage here, so like the value of a car or the value of your home, if that is increasing by a fixed percentage here, the amount y of the quantity, okay, so the value of your home, after t years, you can model this by y equals a times 1 plus r raised to the t power. And it's going to be our job to fill in numbers for a and r, and then we're going to use t to figure out the value of, for example, the home after so many years. Now in this model, a is the initial amount. So for example, if you purchased your home for $200,000, the initial value of your home is $200,000, so A would be $200,000. If you bought your car for, say, $30,000, A would be $30,000. Okay? R is the percent increase expressed as a decimal. So for example, if the value of your home increases by 5% each year, okay, R would be the decimal version of 5%. And if you recall, to get a decimal version, you're just going to take your decimal point and you're going to move it 2 places to the right, which is dividing by 100% per 100. So that's 0.05 is the decimal version of 5%. The quantity 1 plus r is called the growth factor. Now you got to read carefully. Is the quantity increasing in value or is it decreasing in value? Because if it decreases, you're going to use more or less the same equation. It's just that the plus here changes to a minus. Okay? Everything else means the same. It's just that plus changes to a minus. So read very, very carefully. Now in 1900, the population of a town was 5,000. The population increased at an average rate of 2.5% a year, per year. So immediately I see that word increase right here, and I'm thinking to myself, okay, y then is the a times the 1 plus r raised to the t, plus because we are increasing in value. Now, right there, the population of a town was 5,000 in 1900. You can consider that your initial value. I don't see any other population numbers up there. So we can fill in a with 5,000 times 1 plus, and now I need to figure out, okay, well, who's r? Well, r is your right there, your percent increase. So that's 2.5%. But again, we can't plug 2.5 right there. So we need to change this to the decimal version. Move the decimal over twice, and that becomes 0.025. That is 2.5% as a decimal. Now I'm just going to simplify this, and I'll have my equation. Y is 5,000 times 1 plus 0.025 is just 1.025 raised to the t. And there we have it. That's your model right there that you're going to use to answer letters A and B. So if we're asking what was the population to the nearest whole number in 1920, we're asking what is y when t is not 1920 but 20 years after the initial population there. 1920 is 20 years from 1900. So 1.025. And again, I don't want to put 1920 there. That's very, very, very bad. Okay? What you want to do is you're going to say, well, 1920, okay, subtract the initial time there, which was 1900, and so 20 is what we're going to substitute here. And then we're going to go to our calculator. Now I don't have mine up. Let me go get mine. Okay, there it is there. I'm just going to hide that. And I'm basically going to type this in as I see it. 5,000 times 1.025 raised to the 20th power. And so to the nearest whole number, I looked at the decimal, that's an 8. I'm rounding the 0 up. y is 81,931. And so that was the population in the year 1920. Now then it asks, what was the population in the year 1950? Well, we're going to use the same equation, y equals 5,000 times 1.025 raised to the, now 1950 is 50 years after 1900. So 50th power. And so typing that into our calculator, we have the same thing, but raised to the 50th power in this case. And so in the year 1950, the population of the town was 171,855. I looked to the number before, that's a 4, I'm not rounding that 5 up. So 1,700, or 100 rather, 71,855. Okay, so the other one that we're going to be looking at today is a luxury car costing $75,000, and it depreciates. And if you don't know what that word depreciate means, it means it's going down in value. It's going down in value at a rate of 25% per year. So in this case, we're going to be using the equation y equals a times the 1 minus r, because this is going to be exponential decay. Well, cost $75,000, that's the initial value of the car. That's what we're substituting into A. Now we need the decimal version of our rate, 25%. 25% as a decimal. Move that decimal place back 2 spaces, 0.25 raised to the t power. And so our model then is 75,000 times 1 minus 0.25 is 0.75 raised to the t. Now what will the car be worth after 5 years? That means we're going to substitute 5 into t. Y equals 75,000 times 0.75 raised to the 5th power. Now, let's just think ahead a little bit. Remember, your car is depreciating in value, so the value should be going down. So whatever we get, okay, should be less than 75,000. If you're getting a number more than 75,000, you know you made a mistake. So times 0.75 caret 5. And so it looks like after 5 years, the car is only worth $17,797. And I'm going to round to the nearest hundredth there. So I'm looking at the 1. I'm not rounding 85 up. So it is worth, and I'm going to use dollars here, $17,797. Oh, I'm sorry, it says to the nearest dollar. So I'm looking back here, actually at the 8, and I'm going to round that 7 up. $7,798. What will the car be worth after 10 years? Same deal, just substituting 10. Y is 75,000 times 0.75 to the 10th power. So same deal, same equation. We're just replacing the 5 with 10. And so after 10 years, your car, which cost $75,000, now costs a grand total, rounding up, $4,224. Cars are not good investments. All right, so this is just 2 applications of both growth and decay. Make sure you read your word problems carefully to know, am I using the 1 plus or the 1 minus? We have one more to do. We'll be doing that one together at a later date, though. I'll see you guys in the morning.